Hello everyone, myself Ved. Last time we have covered the Claisen condensation and Dickman condensation as well. So today we are going to discuss the rest of the part of Enolate chemistry, and let's start. So here we have a reaction called Michael addition. Michael addition. Suppose you have any reactant molecule like this, and it is treated with a base. First it is going to treat with a base, and suppose NaOH. And second step, we have this conjugated enone. This is very important. This conjugated enone system, what does it mean? It means my double bond is conjugated with the ketone or aldehyde. Makes sense? So this is called conjugated enone. This is one of the most important whenever you are going to talk about conjugate addition. So let me explain something here. Conjugate addition means addition on conjugated system. So conjugate addition is of two types. The one is 1,2 addition and another one is 1,4 addition. So how we can figure out 1,2 and 1,4 position? So always start numbering from the oxygen of carbonyl to the double bond center, like this. So 1, 2, 3, 4. Make sense? So if I am saying my nucleophile, this suppose here nucleophile is going to attack, and this is my conjugated system. Clear? So first you have to mark numbering here 1, 2, 3, 4. If nucleophile attacks at the 4th position, this is called 1,4 addition. And if the nucleophile attacks on the 1,2 position, then this is to number 2 position, then that is called as 1,2 addition. So how can we decide which one is going to attack on the 2 position and which one is going to attack on the 4th position? We all knew nucleophile loves electrophilic center. So we have to figure out in conjugated enone what is my electrophilic carbon. So I think it should be like this. Suppose this is conjugated enone, and we all knew this is the electrophilic carbon here, and this one is my electrophilic carbon. You can mark numbering 1, 2, 3 and 4. Make sense? Suppose I am talking about 1,4 addition. So nucleophile is going to attack on the 4th carbon, and the product will be this. You can mark numbering as well 1, 2, 3, 4. Clear? Do not change the carbonyl bonds double bond. Always attack on the 4th carbon. I am not talking about the mechanism. I am just telling you how we can attach directly without mechanism. And if you are talking about 1,2 addition, 1,2 addition, is this one. Normal nucleophilic addition attack, normal attack. You know that in nucleophilic addition, nucleophile attacks on the carbonyl carbon and CO bond break down and O minus get protonated, and that becomes alcohol. Like this. Suppose here you have a nucleophile. So we are going to attack at the number 2 position. This is 2, this is 3, this is 4. So number 2 is this position, and then this bond is going to break. So it should be like this. Here O minus, here you have a nucleophile. This double bond will remain same, that is not going to affect. And O minus after protonation, suppose you have water molecule, so O minus grab this proton, so it becomes OH. And this is the nucleophile. Clear? So this is the big difference between 1,2 addition and 1,4 addition. You can see this is my 1,4 addition product and this is 1,2 addition product. So 1,2 addition is a normal nucleophilic addition and this addition is like the fourth position is the attacking center. Makes sense? So simply 1,2 addition is given by strong nucleophile, strong, and 1,4 addition is given by weak one. If you have a Grignard, it gives 1,2 addition. And if you have a Gilman reagent like R2CuLi, then that is my weak one, and weak nucleophile attacks on the fourth position of conjugated system. Very simple. Makes sense? And we all knew how we can decide the strong nucleophile and weak nucleophile. Generally, Grignard is, the R part is bonded with the metal and magnesium. So this R is acting as a strong nucleophile, clear? And that is attacking at the number 2 position, nucleophilic addition. If you look at this one, the NaOH is a base. Base loves proton, the acidic hydrogen. We all knew this carbon has 2 proton. So one of the proton is going to grab by this base. So here you have a negative charge. Makes sense? This is the negative. And now you know that this is acting as a nucleophile here. This is my nucleophile. So you should know this nucleophile, is it strong or weak? Whenever negative is conjugated, whenever negative is a part of resonance, then that is treated as a weak nucleophile. We have learned the nucleophilicity. I discussed with most of my students in one-on-one sessions how we can decide a nucleophile in weak and a strong. So generally few things we have to know. The first, whenever you have a negative charge, then that is called as a strong nucleophile except the resonance condition. Second case, whenever you have non-conjugated negative charge, that is also a strong nucleophile. What is weak? Weak are generally lone pair and neutral one. These are considered as weak nucleophile, clear? So this negative is a conjugated one. So this one acts as a weak one. So this weak and this is conjugated enone. So addition is what? 1,4 addition. So you have to attach this nucleophilic carbon, the number 4th position of the conjugated enone. So like this. This is my conjugated enone. This is 1, this is 2, this is 3, this is 4th carbon. And 4th carbon is directly bonded with this carbon. So suppose this is my carbon. And this carbon has diketone, the left and right, like this. Double bond O, double bond O. Makes sense? If you are going to take orgo 2, then you have to solve this one with mechanism. But in DAT, there is no need to know the mechanism. Clear? So simply you can say this is the 4th position attack. That is called 1,4 addition. Any doubt? Tell me. This is also called as Michael addition. This step is called as Michael addition. This is called as Michael addition as well. I have one more question. Oh, we use this one. Suppose we have this. Take your time and let me know what it should be the answer. So first of all, we should know what is the NaOH. NaOH is a base. Base will grab the acidic hydrogen of this diketone. Okay. So we know that these are the protonated, this one is a proton. So base will grab this proton. So it becomes a nucleophile, which is a weak nucleophile. Why weak nucleophile? Because it is conjugated. And now we can do the numbering here 1, 2, 3, 4. So this is a weak one, so it attacks at the 4th position. So simply the product will be this. This is supposed to be my 4th carbon. And now 4th is bonded to 3. 3 is bonded to 2, 2 is bonded to 1. Makes sense? Simple. So this is the product. Clear? It can be asked like in your exam in multiple type of question, like this is the reactant, this is the product, and they can say how many ketone molecule in the product. Make sense? So as you can see 1, 2 and 3, we have 3 ketones. So a lot of question can be asked here. I am going to give you one more question which is very interesting. Suppose we have this CH3 bromine. The first step is treated with magnesium in the presence of ether. Second step, we have this conjugated enone with water as well, means third step you can use here H2O. So what should be the product? So look at here, magnesium and we have alkyl halide, so it will form a Grignard. Magnesium insert between carbon and bromine bond, so it will form CH3 MgBr. We all knew CH3 minus is my nucleophile and we have conjugated enone. We all knew this is a strong one and this is conjugated enone, so it attacks at the number 2 position as a nucleophilic addition like this, in this way. So this negative attack over here, this bond is going to break. So it will be O minus and here we have CH3 and this is the double bond. In the next step, we all knew we have a water, so it will grab the hydrogen of water. So here we have alcohol, OH, and this is CH3. Makes sense? So this is called as 1,2 addition. Grignard is my reactant molecule. So now the next is, this is the, we have slide here. We have already covered the aldol one. We have covered the aldol. I discussed what is enolate. We have done the aldol condensation. In aldol condensation, the product is alpha beta unsaturated carbonyl compound and an intermediate product is beta hydroxycarbonyl. So you can see this is beta hydroxycarbonyl. Here we have some questions. This one is a Claisen one. Last time we have done the Claisen. Claisen, we have covered 3 types of Claisen. The one self, second crossed Claisen, okay, and the third one is intramolecular Claisen. Ultra is also called as Dickman condensation. Now this is the very important, the Malonic Ester synthesis. Malonic Ester synthesis. But before moving to this equation, I want to discuss a step which is called hydrolysis. So you should know what is the hydrolysis of ester first of all. So let me discuss this. Suppose you have a reactant molecule ester and we are going to hydrolyze this. For hydrolysis we can use H3O plus or we can use H plus H2O. Both are same thing. Look at the trick how we can draw directly hydrolysis product. So whenever you have ester molecule, so look at this bond. Sorry. Look at this one. This is the ester, and we used here H plus H2O or H3O plus. So this is the polar bond, okay. CO bond is a polar bond, oxygen is more electronegative and carbon is less electronegative. And you can use here HOH molecule, water, HOH. We have a single bond, that's why we can use here 1 mole of water. And the simple thing is that we all knew the charges on water is what? H plus, O minus. And this carbon oxygen is what? Oxygen is minus, carbon is plus. So less electronegative means oxygen is more. So oxygen will grab the less electronegative part of water. Clear? So this O minus is going to grab this H. And this CO bond is going to grab this OH molecule. So as a result of it, we have carboxylic as well as alcohol molecule. Clear? So hydrolysis of ester produces carboxylic as well as alcohol. Makes sense? So this is the best way to draw the hydrolysis product. And you know, most of the reactions you can do hydrolysis in such a way. If you have a single bond. If suppose you have a double bond, then you can use 2 mole of water. If you have a triple bond, then you can use 3 mole of water. In this way, suppose we have RCH2NH2 and we have to do the hydrolysis of this amine. Basically this reaction is the part of carboxylic acid derivative, but it is important in malonic ester synthesis, that's why I am discussing this. So we can use here H plus H2O again, or H3O plus, and we can write here HOH. So nitrogen is going to grab the hydrogen because nitrogen is more electronegative between carbon and this is less. So like this, and this CH2 will grab OH. So as a result of it, we have RCH2OH and ammonia. Okay. Rest we will discuss in the carboxylic acid derivative, in which I will discuss acyl chloride, ester, anhydride, carboxylic acid as well as nitrile. So look at this equation first. We have a reactant molecule which is a diester, which is also called malonic ester. Okay. So in malonic ester we have 2 ester sites like this. We can zoom this one a bit. Okay. You know, you can, if you look at this entire equation here, couple of things is important. If you are familiar with SN2, if you know how a base is going to grab a proton, then you can apply all these informations in this equation. Generally, most of the student thought process is like we have to directly jump in the reactions without knowing the basic information, and that's why you are struggling. So first of all, if you are going to learn the organic chemistry reactions, you must have to know the basic things like what is base, what is nucleophile, what is the attacking center and all. So this is a NaOR, which is a base, O minus Na plus, makes sense? Na plus O minus, like this. So base is going to grab the acidic hydrogen. We all knew this hydrogen is acidic. So base will grab any one of the acidic hydrogen and you have a negative charge. This is enolate. This is enolate, which is a negative charge. And the next mole is my alkyl halide. We all knew whenever you have alkyl halide and nucleophile, you should know this reaction. This is the alkyl halide and this is a nucleophile. If suppose nature of the reaction is SN2, then nucleophile attacks over the R part and X leaves. Same here. Nucleophile attack on the R1 and X leaves, so you have R1 substituted here. Clear? We can see here we have 2 acidic hydrogen, so one more time it is going to deprotonate. And look at here, we have again a base and there is a 1 hydrogen, so base is going to grab this hydrogen. Again you have a negative charge, again this is enolate, and again you have 1 mole of alkyl halide. So nucleophile attack on the R and X leaves. So this is SN2. So now you have both R1 and R2 bonded to this carbon. Clear? Makes sense? Now this third is, listen, this is step by step. First it is going to hydrolyze, means first hydrolysis and then heating. You cannot say like both occur simultaneously, no. The first hydrolysis, we all knew ester hydrolysis produces acid. So this side we have ester, this side we have ester. So you should first draw, the hydrolysis will produce both molecule as a acid like this. C double bond OH, a carbon have R2, R1 and then again carboxylic like this. Clear? This is the hydrolysis product. And now if you are going to heat this, what is the heating effect? Heating is called decarboxylation, which means removal of CO2 group. So if you remove any of the CO2 means carbon dioxide, that is also called decarboxylation. So if you remove the CO2 molecule, this is the CO2. Suppose you are going to remove this CO2, any side, it doesn't matter. So you can see you have a hydrogen and this hydrogen is bonded to this carbon. So carbon R1, R2 and one side COH will remain same because only one side is decarboxylation. So you have a carboxylic acid as a product. And here you have a hydrogen. If you balance this, this is the bond line form like this. Same here. Makes sense? I can give you a question based on this. Look at here. Suppose wait. like this. Make sense? So this is my diester. The first step is a base, then alkyl halide, again base, again alkyl halide, and the last step is hydrolysis with heating. So let's do one by one. We all knew this one has a 2 acidic hydrogen and the base is 2 times, you can see. So if suppose there is a 1 negative charge, then negative attack on the CH3 and bromine leaves. It means in place of a hydrogen you have a methyl group in the first step, this step. You have a hydrogen here, so you have to keep a methyl. Second, base is again going to grab this hydrogen and then again it becomes a nucleophile and it attacks over this ethyl bromide. So one side you have a ethyl chain and one side you have a methyl chain. So we can directly write down from step 1 to step 4 like this. In this way, we can say this is CH3 and this is CH2CH3. We can do the bond line like this. Make sense? So this is ethyl, this is methyl. And now the next is hydrolysis. We all knew this ester is both are ester. So we can directly draw the carboxylic here. One side you have methyl, one side you have ethyl. and next is heating. So any of the carboxylic, we have to remove its CO2 part. Suppose this is the CO2 here. So what is left? C double bond OH, carbon, carbon, and here we have a hydrogen. This is a methyl. This is a ethyl, like this. Clear? You can see. So this is malonic ester synthesis. Next is acetoacetic ester synthesis. In this synthesis, we can use acetoacetic ester. We can use acetoacetic ester, this ester molecule. Acetoacetic ester. So again we have a base and again we have acidic hydrogen. Clear? So look at here, the acetoacetic ester synthesis prepares methyl ketone from acetoacetic ester. The reaction mechanism is nearly identical to the above mechanism for malonic ester synthesis. However, the starting material is beta ketoester. This is also called beta ketoester, which is acetoacetic ester. While the malonic ester synthesis, acetoacetic synthesis reaction to seem complicated, we can simplify them into 4 important steps. First, enolate, second, alkylation, third, hydrolysis, and fourth, decarboxylation. Note that enolate formation and alkylation can occur once to add one alkyl group to the alpha carbon of the compound or twice to add 2 alkyl group. Remember that hydrolysis of ester with aqueous look at here. Ester hydrolysis produces carboxylic. If a carboxyl group is beta to the carbonyl group, then addition of heat will result in decarboxylation. In this reaction, one carboxylic group leaves the compound as CO2. Decarboxylation is entropically favorable at high temperature. So simple thing is that base is going to grab this hydrogen. Here you have a enolate negative attack over this R and X leave, so you have R. But here you have to introduce just 1 mole of alkyl halide. If suppose 2 mole is given, then you can use both. Hydrogen is replaced by the alkyl group. It's your choice. It's depend on the given reaction. Make sense? So here you have just one alkyl molecule because only one alkyl halide is used. Next step is hydrolysis. We all knew ester hydrolysis produces carboxylic. So this is my ester. So here you have carboxylic. And then the last step is heating. We all knew whenever you have acid and you are going to heat this, there is a removal of CO2 molecule. So we can remove this CO2. So you have this ketone, still we have C double bond OC and then R like this. Because here you have a hydrogen left. Clear? This is called beta ketoester, which is acetoacetic ester. Here we have 2 important points. Let me explain this. This one is a malonic ester, and once you hydrolyze this, both ester becomes acid, you can see. And once you heat this, any of the removal of one CO2 molecule, so we can remove either left or right, doesn't matter. So you have still a carboxylic here. While in the second one, in acetoacetic or beta ketoester, if you hydrolyze this, ester becomes acid. And once you heat this, there is a removal of CO2 from this mole and you have this one. Clear? So malonic ester gives you acid and acetoacetic ester gives you ketone. Clear? So this is the big difference. We have done this type of reaction already. You can see NaOR here, base R1X and then R2X. So simply we can say this is my R1, this is my R2, and then hydrolysis and heat. So both acid is hydrolyzed to give you carboxylic, and one of the carboxylic we have to remove its CO2. So one COOH here. This is beta ketoester. This carbon is alpha, this is beta. So again base R1 and R2 both you can see here. So we can draw like this, R O C double bond O C double bond O, this is R1, this is R2. Clear? Next step is hydrolysis. So we can hydrolyze this ester into acid. So it should be like this: COOH, R1, R2, and then ketone. And the last step is heating. Heating means removal of COH, CO2. So you have this carbon with R1, R2 and a hydrogen. You can see R1, R2, carbonyl, and here we have hydrogen. Here we have few more questions for practice. You can take your time and try this. 1,4 addition, we have done this already. Let me explain this again. So I said that 1,4 addition, do not apply this one. Do not follow this. Just put the numbering on the conjugated ketone 1, 2, 3, 4 like this: 1, 2, 3 and 4, and nucleophile attacks over the fourth carbon, and this double becomes single. You can see 1, 2, 3, 4. Clear? So this is called 1,4 addition and it is given by a strong nucleophile. Clear? Next, which type of nucleophile can give you the 1,4 addition? So you can see this negative is conjugated, that's why weak. This is also conjugated because double bond have a lone pair. This is also negative conjugated because C triple bond, and here we have, and this is in resonance, and this is also R2CuLi. This is also a weak one. Okay. While if you look at this one, this is the acceptor. Acceptor means conjugated enone. Generally we have to cover conjugated ketone, but sometimes we have more than a different kind of conjugated system. Look at this. This is conjugated enone, this is conjugated, this is conjugated, and CN also conjugated, and this NO2 is like this. So this is also conjugated system. Clear? So this is a donor, this is an acceptor. So this is also called Michael addition. Okay. Simply we can attach this one here, just 1, 2, 3 and 4, and you can see 1, 2, 3 and 4. Simple. Clear? Next is organocuprate R2CuLi, which is also called Gilman reagent, We have done the Gilman case as well, R2CuLi. This is very, very important. Look at here. Let me explain this here. Look at here. Suppose you have this conjugated enone and we have this nucleophile CH3 twice CuLi. This R2CuLi is my Gilman, in which R2CuLi you have to consider only one R, one carbon chain as a nucleophile, not both. So here R minus is my nucleophile. So similarly from here we have CH3 minus is my nucleophile, and it gives 1,4 addition. So CH3 attack the fourth position. So we can say the product will be like this, the methyl. Make sense? That one. If you have this example, you can see this is CH2, this is CH3. So this is ethyl, you have ET twice CuLi this is. So you have to consider ethyl 1 is my nucleophile, CH3 CH2 minus, and that attacks at the number 4th position. You can see 1, 2, 3 and this is the 4th. Other reactions at alpha position. Alpha halogenation, there are two conditions for alpha halogenation. One the basic and another one is acidic. All alpha hydrogens are replaced with halogen atom in acidic condition. Sorry, in the basic condition, because base loves proton and all the alpha H is the acidic proton. Like this, suppose you have look at this one. You have, suppose this is carbonyl. So what is the alpha position? Alpha is a neighboring position to the carbonyl group. So this is alpha, this is alpha. Here you have 2 hydrogen, here you have 2 hydrogen. And medium, suppose here I am saying NaOH and Br2. We all knew NaOH is a strong base, so it means the medium is basic and Br2 is my halogen. So all the alpha hydrogen is replaced by bromine, and that is called as basic condition. So my product will be this. Here Br, here Br, here and here as well. Clear? If you have acidic medium, then only one alpha hydrogen is replaced by a replaced by base. Okay, means halogen. Like this. Suppose we have this one and we are using here H3O plus Br2. So this is the alpha, this one is alpha, both alpha is same here. So any one of the alpha hydrogen is replaced by bromine. So this is called reaction in acidic medium. Clear? Next, the haloform reaction, which is very, very important. So first of all, you should know what type of reactant can give haloform reaction. So I can say here ketomethyl, like this. So here we have few reactant and we have to figure out which will give haloform test or haloform reaction. I told you ketomethyl means this type of connectivity. CH3, C double bond O and this. Whenever we have this kind of connectivity, it gives haloform test. So you can see here COCH3, COCH3, COCH3. While this one has no, this one as well. So these two cannot give haloform and this one will give. Haloform, which is very important. This kind of CHX3, this is called haloform. X can be chlorine, bromine and iodine. Generally these three are more popular one, not fluorine. So if you are going to keep here chlorine, this is called CHCl3, which is my chloroform. If you are going to here keep bromine, then this is called bromoform. And here if you are going to keep iodine, this is called iodoform. Okay. So in haloform reaction, what is my reagent? Reagent is X2 excess NaOH with hydrolysis. This is important. X2 we can use here Br2, Cl2, I2. Clear? Suppose we have this one. I am saying CH3, C double bond O, CH3, and we are going to use here Br2, NaOH, and hydrolysis. So look at here, this any side, either this or this R part, this part will give you haloform, this part will give you haloform. In place of X we have bromine, so we can make its bromoform, and we all knew the bromoform formula is what? CHBr3. And the rest of the part, this part is going to oxidize, this is going to oxidize into carboxylic like this, CH3, C double bond OH like this. Make sense? Simple. If you don't know how to draw the product with trick, you can see Na plus OH minus. So one side you have to attach bromine, one side OH. So this side, the CH3 side will grab this bromine, so form bromoform. So rest of the part is going to connect with OH. So you have carboxylic. Clear? Suppose you have this one. Excess and here hydrolysis. So simple, we can say this CH3 is going to form chloroform, and we all knew chloroform is CaCl3, and the rest of the part is what? This part is going to oxidize, means OH. So C bonded with OH, so here you have carboxylic. But it should form a carboxylate ion, not carboxylic, because medium is basic. So base will going to deprotonate this. So it should be like this, O minus Na plus, in this way. You know, both are correct. It depends on your given choice. Okay, if you have this one, then you have to select this. If there is no carboxylate, only carboxylic, then you can go with carboxylic. Both are correct. Okay, next is alpha deuteration. Look at here. Alpha deuteration is similar to alpha halogenation, but instead of replacing alpha hydrogen with halogen, alpha hydrogen are replaced by deuterium atom. Like alpha halogenation, alpha deuterium occurs in basic as well as acidic condition. Again, in basic condition, if you have a base, then all the deuterium is going to replace the alpha H. If you have a medium is acidic, then deuterium is going to replace only one alpha H, like this. Suppose you have this cyclopentane ring, and I am saying here suppose OH minus with D2O. So we all knew this is a basic medium, and how many alpha H you have? 4. So all the 4 alpha H is replaced by deuterium. Makes sense? And if you have medium is acidic like H3O plus D2O, then deuterium is replaced only one alpha H, and the product will be like this, deuterium. This is an acidic medium. Clear? Next, this is simple one. You can see Br2 NaOH with H3O plus. This is my haloform test, and this is the keto methyl. This is methyl here. So methyl is going to convert into bromoform because we have bromine. So it forms CHBr3, and the rest of the part, this entire part is going to convert into carboxylic, C double bond OH, then ring, and here methyl, like this. Clear? So this is all about the enolate chemistry, and we have done this. This is the last, we have covered the enolate in 3 parts. The lecture 1 is all about the aldol condensation, lecture 2 is all about the Claisen and Dickman condensation, and the lecture 3 in which we have covered the rest of the part of enolate chemistry. Maybe in the next session we can discuss questions of enolate. So please share and subscribe, share with your friends, and go to the comment box. If you really like this video, please say something about the video, and thank you so much again.